So sometimes when we do a chemical reaction, one of the reactants is a gas or one of the products is a gas. And so instead of measuring the mass, we would measure the volume, the temperature, and the pressure. We can calculate the moles using the ideal gas law. So from the ideal gas law, the moles of gas would be the pressure times the volume divided by R times the temperature. So for stoichiometry, when we're calculating amounts of reactants and or products, grams to moles to grams. So that's what you chant to yourself when you do stoichiometry. Grams to moles to grams. Grams to moles to grams. Every stoichiometry problem is a variation on that theme. So this is a variation. If you're having a gas, instead of a mass, you're going to have a volume, a pressure, and a temperature. Instead of using molar mass to convert to moles, you're going to use the ideal gas law to convert to moles. So that could happen for the starting substance or the ending substance. It's just a variation. So in this reaction, 4.58 liters of oxygen were formed at 745 millimeters mercury and 308 Kelvin. How many grams of silver oxide decomposed? Use the chemical equation to help you organize the information. So 4.58 liters of oxygen. So that's something about the oxygen. And we've got a pressure there, 745 millimeters of mercury. And the temperature, that's also of the oxygen. And the question, how many grams of Ag2O? Question mark, grams. So I'm going to use the space way up at here at the top. Normally we would do grams to moles to grams. And we'd start with grams of oxygen to moles of oxygen to moles of Ag2O to grams of Ag2O. And we are trying to find grams of Ag2O, so that's fine, but we're not given grams of oxygen. So instead of grams, we've got the pressure, the volume, and the temperature. We're going to use the ideal gas law to convert to moles, and then we can jump in with regular stoichiometry. So to use the ideal gas law, are these units good? No. Volume and temperature are fine, but the pressure isn't. We need to convert this to atmospheres. 1 atmosphere, 760 millimeters of mercury. Those cancel out. 745 divided by 760. 0.980. 3 significant figures, write down 2 extras, and that's atmospheres. So I'm going to calculate over here, the number of moles is equal to the pressure times the volume divided by R times the temperature. So the pressure, 0.98026 atmospheres. Oh, I don't have enough room. I'll just make it work somehow. 4.58 liters. So a droopy calculation. 0.0821, whoops, liter atmospheres per mole Kelvin times the temperature, 308 Kelvin. Again, we got 2 numbers in the denominator, so if you want to multiply down there, you got to use the parentheses. So 0.98026 times 4.58 divided by, open parentheses, 0.0821 times 308, close parentheses, equals. So n is equal to 0.1, let's try that again, 0.177, 3 is the smallest number of significant figures, write down 2 extras, moles of oxygen. We are now here. We got to moles of oxygen. We need to go to moles of Ag2O to grams. So I'm going to multiply. I want to get to moles of Ag2O divide by moles of oxygen. And then I need to get to grams of Ag2O, and I'm dividing by moles. Mole to mole, this is a mole ratio from the balanced chemical equation. This is saying that 2 moles of Ag2O produce 1 mole of oxygen. So 2 moles of Ag2O for every 1 mole of oxygen. The last one is molar mass. So look at the periodic table, find the mass of silver is 107.9. We got 2 of those, 2 times 107.9 plus an oxygen at 16.00, 231.8, 231.8 grams per mole. In my opinion, you should never round molar masses to less than 4 significant places. Okay, don't round them to the nearest whole number. It's just not a good idea. Okay, 0.17754 times 2 times 231.8. Looking at sig figs, 3 sig figs, 82.307, 82.3 grams of silver oxide. Any questions? So we took a stoichiometry problem, like you learned in Chapter 8, and we put in an ideal gas law problem, and we put them together. That happens. So we have something called standard temperature and pressure. It's abbreviated STP. Standard temperature is 0 degrees Celsius or 273 Kelvin. That's the temperature at which water freezes. And the standard pressure is 1 atmosphere. That makes sense. That's, just sea level, regular pressure. You need to remember those. Okay, I think they chose 0 degrees Celsius as standard temperature because it's easy to achieve. If you want a gas to be at standard temperature, you take its container and you submerge it in ice water. No technology needed. You don't even need a thermometer. It's going to be at 0. So that's easy. If you want the pressure to be 1 atmosphere, you make sure that it's the same pressure as outside. Also, very easy. So let's calculate the volume of 1 mole of gas at STP. So we've been calculating things like that. So the volume would equal N, that's a weird N, RT over P. So calculate the volume of 1 mole. Well, what's N? It's 1. 1 mole. And we're going to say that's exactly 1 mole. Then we have R, 0.0821 liter atmospheres per mole Kelvin. Times the temperature. What's standard temperature? It's written right there, 273 273 Kelvin. Divided by the pressure, standard pressure, 1 atmosphere. So these units are working out. Atmospheres and moles and kelvins all cancel out. So we have 1 times 0.0821 times 273 divided by 1. This would have 3 sig figs, 22.4. Unit is liters. So at standard temperature and pressure, 1 mole of a gas occupies 22.4 liters. So 22.4 liters is a cube about this big on a side. So, you know, it's big. It's like a really big moving box. But you could carry it, right? A box that size. The molar volume of an ideal gas at STP is 22.4 liters per mole. This is the volume of 1 mole. 22.4 liters per mole of gas. That's going to be true of any gas at STP. So here we have illustrations, a mole of helium, a mole of xenon. The volume of 1 mole of helium at STP is 22.4 liters. The volume of 1 mole of xenon at STP is 22.4 liters. These atoms are larger. Does it matter in how much volume they take up? No, because there's so much space that's empty between them. This is people in Wyoming, okay, not people in the elevator. Is the mass of this sample different than the mass of that sample? Yes, it is, because these particles weigh more. We have the same number of particles. How many particles? 1 mole. 6.022 times 10 to the 23rd. We have Avogadro's number. Obviously, that's not how many are in this box. We have Avogadro's number of helium atoms here, Avogadro's number of xenon atoms over here. They take up the same space, but they don't weigh the same. You okay with that? The reason they can take up the same space is because both of those samples are mostly nothing, mostly empty space. Okay, so the volumes are the same. So that molar volume makes these stoichiometry problems much simpler. So anytime you see at STP, you can use that conversion. If it's not at STP, you can't. You can't use it everywhere. Yeah?
Most likely for all our questions, it's going to be in STP.
Most of them are going to be in STP.
So what if it's not?
Well, if it's not, then we have to do what we did. Nope, not there. What we did here. So you have to use the ideal gas law to calculate the number of moles. So there could be a problem like that on the exam. But mostly in Chem 3A, we're nice to you. I know you think we've been mean, but we're actually being nice. In Chem 1A, the gloves come off. So here, this one, stoichiometry. How many liters of oxygen are required to form 10.5 grams of water? The magic, I guess this STP isn't a word. Anyway, the magic thing at STP. So that makes things easier. So 10.5 grams of water. So I'm going to write that here, 10.5 grams of the water. And the question is how many liters of oxygen? Question mark, liters. So normally we would do grams to moles to grams. Here we're going to start with grams of water. We're going to go to liters of oxygen. So grams to moles to not grams, we're going to liters. But instead of needing to use the ideal gas law, we can use 22.4 liters per mole. So 10.5 grams of water. Go to moles of water. Go to moles of oxygen. Go to liters of oxygen. Previous unit comes to the denominator, grams of water, so those cancel out. Moles of water, so those cancel out. Moles of O2, so those cancel out. Need the molar mass of water. We've used that one a lot. That's 18.02. The mole ratio is the coefficients here. 1 mole of oxygen, 2 moles of water. So I put a 1 in front of moles of oxygen and a 2 in front of moles of water. At STP means I can use the 22.4. Sometimes students get confused and they put 22.4 moles per liter. It's the molar volume. That means it's the volume of 1 mole. Just like a molar mass, it's the mass of 1 mole. So the mole gets the 1. 1 mole takes up 22.4 liters. 10.5 divided by 18.02 divided by 2 times 22.4. Um, 6.52, 3 sig figs. The unit is liters. Going to round that to 6.53 liters of oxygen. Any questions? We've done a lot of problems today, and I've done them fairly quickly. They'll all be on YouTube. And so a good way to practice these, pull up the video, get to the part where I just show the question, pause. Do it yourself. If you get stuck, start the video and watch until you're like, oh, okay, and pause it again. Do that until you can do all these questions first time without any help. Okay? It's a good way to practice.